This is lecture 42. In this lecture, we're going to talk about Brownian motion. So I'm going to give you the idea of what it is and also give you some formal definitions for it. Okay, so the concept of Brownian motion is also called the random process. Is it just a diffusion process which comes from a random walk model? So I have a couple animations here. Let's see if these will actually load. This one may not load. Okay, so here it goes. Okay, so this is an illustration of Einstein's explanation for Brownian motion. So basically, the idea here is that this ball is showing Brownian motion. So the way that you can think about this is a bunch of little particles are coming and basically hitting the ball, so it kind of moves back and forth. And so you can like if these little particles were atoms or molecules. And so this gives an idea of the Brownian motion. And actually, if you look at this looks a lot like, you had that the spider model. So this looks a lot like the movement of the spider model, where it's not following this exact path. It's kind of getting a little bit stuck as it's trying to go on a path, and so it's being kind of pushed around. So this is one of the ideas of Brownian motion. So this is a little motion that you can click on here. So let's go back to our slideshow. And then here is another one. So let's run this application, and this actually gives us two different ways that people have looked at it. So one was by this botanist Brown, and so he noticed that the grains of pollen suspended in a liquid move erratically. And so he called that Brownian motion. And then again, Einstein, which is what we kind of saw already, was explained the motion by having this mental picture of those little particles that were hitting it. So here, this is Brown's idea, is that that the grains of pollen suspended in a liquid, it moved erratically. So here we can go down here and we can get to graph this. And so here, if we look at the graph of what's happening, this is the same sort of thing that you saw on the previous slide. And so this is what Brown noticed in 1827, and then Einstein here put this picture that we saw basically before on this put this idea of all these particles basically crashing into this larger one. And so again, this is similar to the previous slide that we saw. Okay, so that gives you a little bit of a visual of what Brownian motion is. And so we actually start with a random walk. So I told you on this slide that Brownian motion is really thought of as a diffusion process that comes from this random walk. And so what we're going to do is we're going to start off talking about a random walk. So here, this is a diagram of a random walk, where basically you can think about if you're in one state, then you can move right with the probability of P, and you can move left with the probability of Q. And this is what we've seen before. We saw this in discrete time Markov chains. So if we let U of xt be the probability that we're at state space X, then this is kind of what we did when we were talking about discrete Markov chains. We can say that U of xt satisfies the diffusion equation. So what we're going to do is we're going to actually take this U of xt, so basically the probability that xt is equal to x, using this idea of this random walk, and we're going to derive the diffusion equation. And then basically this is going to, under certain conditions, give us what we term Brownian motion. Okay, so think about U of xt. So what's the probability that you're going to be at space x? So if at state x. So here, if I'm at state x, then I could have come from x minus delta x, so from x minus this previous thing, with a probability of p. So I could have come from a lower one with probability of p, or I could have come from a higher one with the probability of q. So this is our u of xt plus delta t. So at the next time, what's the probability that we're at state space S? What's the probability that we came from the lower state plus the probability that we came from the upper state? So again, this is just what I said. This part's moved from the left and moved from the right. Okay, so now we're going to apply Taylor's formula to this. So if we look at this and apply Taylor's formula, basically we're going to expand this u of x minus delta xt using Taylor's formula. So this is something that you've seen before in calculus. So here we expand the u of x minus delta xt in this way, and then similarly u of x plus delta xt in this manner. And just combining like terms, we can have, here we have our u of xt, because remember p plus q gives us 1, right? So what's the coefficient in front of u of xt? It's just p plus q, which is 1. Here in front of our partial with respect to x, we have a negative p and a positive q. So here's our q minus p. Our second derivative, we have a p plus q, which again is 1, because remember the sum of the probabilities adds up to be 1. And then we have some higher order term here. So what we can do is we can take our u of xt plus delta t minus our u of xt divided by delta t, and we get this. So this is just from the previous slide. So if we let c be the limit as delta t and delta x go to 0 of this part, and then d be the limit as delta t delta x squared of this part, then what we have is we can rewrite this. This part gives us a partial of u with respect to t. This we had was these two terms here are combined to be our c times our partial with respect to x, plus this, the limit here was our d over 2, so here's the 1/2, times our second partial with respect to x. And so again, this is just the diffusion equation with drift, where here d is the diffusion coefficient and c is our drift term. So here was what we just derived on the previous slide. So if we let there be equal probability of coming from either the left or the right, then what we get is that our c term is equal to 0, which gives you what we term Brownian motion. So basically there's an equal probability of moving in one direction or the other if you're at a certain spot. So Brownian motion satisfies this diffusion equation in which we have no drift. And so it can be thought of as the motion of a particle which diffuses along some line. So if we this is one visual of the Brownian motion. So at each point t, the particle's position is normally distributed. So here's this normal density curves are superimposed. So we can think about this as the particle's position is normally distributed about the line with some variance t. And the variance gets greater as t increases. So here, if our initial condition is given to be x0, then we can solve the diffusion equation and we get the probability of xt equals x, or our u of xt is given by this form. But remember what that form is. We've seen that form before. This is just the probability density function for the normal distribution, where here we have x0 plus ct is our mean, and dt here is our variance. So the standard Brownian motion or Wiener process assumes that our initial condition is 0, and again that we have p equals q equals 1/2, so our c is equal to 0, and our d is actually equal to 1. So our standard Brownian motion has this probability density function, which is just the normal distribution with mean 0. So formal definition of a Brownian motion or a Wiener process is that it's this stochastic process that depends continuously on t, so it depends continuously on time. It is a real number between negative infinity and infinity, and the following conditions hold. So the probability that we start at 0 is just 1. It also satisfies the normal distribution, so it has a normal distribution with mean 0 and variance t. has stationary increments. So basically what that means is if we take W of T2 minus WT1, then this is normally distributed with mean 0 and variance T2 minus T1. It also has independent increments, so basically if I think about two different increments from T0 to T1 and T2 to T1 to T2, then these are independent. So because of stationary increments, we have that the variance of our change in W can be written as the variance of W of T plus delta T minus W of T. So this is just our change in W here. And so we end up getting the variance for W T plus delta T. Remember, that is just T plus delta T because it's normally distributed with variance whatever's inside here. And the W of T has variance of T. So we get the variance of delta W, or expected value of delta W squared, is just delta T. So we normally think about the change in W, or dW, is approximately the square root of dt. Okay, so remember the examples that we talked about in the last lecture. We had these examples of a stock or a stochastic logistic growth, spider movement, and climate variability. So remember all of these here, we had this Joyner process in here. So we had the Joyner process showing up somewhere, or this Brownian motion coming in. So in general, a stochastic differential equation has this form: the change in our variable x is equal to some function alpha, depends upon t and our x, times dt, plus this part that has our Joyner process involved. So here's the Joyner process dw here. So if we're looking at the solution, just like when we could look at the solutions of our ordinary differential equation, we can actually look at solutions of our stochastic differential equation. For very simple models, we can actually look at the solutions. And so if you were looking at the solution, this is the general solution. So x of t, just think about integrating each of these terms. The thing that's different is this first term is our standard integral that you think about, that you learned about in Calculus 1. But the second one, we're integrating with respect to this Joyner process. This is what's called our stochastic integral. And so this one has a slightly different definition than what the standard Riemann integral is. So what we're going to do next time is I'm going to give you a brief overview of the stochastic integral. We're not going to go into depth about basically stochastic calculus, but I'm going to give you a broad overview of it just so that you get a sense for what is stochastic calculus, what is the difference between stochastic calculus and regular calculus, but we will not go into a great depth, but we'll do that next time.